So in today's series of lessons, we're going to delve into thermodynamics. It's one of the more challenging topics we'll cover throughout the year. Not something I wanted to try from home, but if the thermodynamic blues get you down, don't worry, refer back to the video and we'll get through it. So I'm looking at worksheet 3 today. Table I for today. Let's take a look at a couple equations here. If I look at the first equation, methane plus oxygen goes to carbon dioxide and water. This is like lighting a Bunsen burner here. It says delta H is negative 840.4 kilojoules. That tells me, and this table I is nice enough to say, the minus sign indicates that it's an exothermic reaction. So this means energy is released. Which means it would appear as a product. It does not appear as a negative number in the equation. You just say and 890.4 kilojoules. If I look a little bit further on down table I, H2 gas plus I2 gas goes to 2HI gas. That's right down here. It says delta H, it's positive 53.0 kilojoules. That means this is endo. I'm absorbing energy. Goes on the reactant side. And 53.0 kilojoules. So the negative sign tells you which side of the equation you're going to put the energy on. But in the equation, the energy is always a positive value. Now, table I is written in such a way that these delta H values are applied stoichiometrically to each of the reactants and the products. So what do I mean by that? It's just another part of the equation, it's just another term, so it's 890.4 kilojoules for every 2 moles of water formed, or for every 1 mole of carbon dioxide formed, or for every 2 moles of oxygen used, or for every 1 mole of methane used. So if I look at propane, it's a little bit further down the road here, somewhere in here. It's the second equation. My stoic is 1 to 5 to 3 to 4. Delta H is 2219.2 kilojoules. So, well, what if you had 2.5 moles of propane reacting? How many kilojoules would you release? Mind you, delta H was negative on table I, so I just put the equation energy term on the right. I didn't put it in there as negative, I just said and 2219 kilojoules. So stoic says, well, start with what you're given, 2.5 moles of propane. There's 1 mole of propane, it gave me 2219.2 kilojoules. Roughly 50 kilojoules, 3 sig figs there. A little off frame, I'm going to move over a little. I'll drop the phone. Alright, well, second example. What if I had 8.00, try to keep 3 sig figs there, moles of CO2 formed? How many kilojoules would you release then? Start with what you're given. 8.00 moles of CO2. 2219.2 kilojoules for every 3 moles of CO2. Round it to sig figs, it's roughly 5920 kilojoules. So that's pretty straightforward in terms of the energy. That's actually an improvement on this table compared to our supplemental ones. But we'll get there. Okay, so you're going to have to do some stuff like that on worksheet 3, placing the energy on the correct side of the equation here. And then there are questions like down here at the bottom. What if you had 4 moles? Yada, yada, yada. There's a little bit of that. Okay, so we're going to start thermodynamics. Hang on to your hats. Keep your hands and feet inside the ride at all times. Do not pass go. Do not collect $200. I told you this before. If I did anything in my life succinctly, it was come up with 4 words to sum up the first 2 laws of thermodynamics, and they are energy bad, chaos good. So the first law of thermodynamics refers to enthalpy changes, potential energy changes. And it says something like, it is favorable in nature to get to a state of lower potential energy. So you don't put your bowling ball on top of the refrigerator. That's not a good place to store it. Eventually it's going to fall down and hit you in the head. It is favorable to release energy. Exothermic processes are favored in nature. Negative delta H is favorable. Okay, so that's law number 1. So you don't want energy. It's favorable to get rid of energy. I don't want energy. Get rid of energy. Energy bad. Thermodynamics law number 2 says something to the effect of, it is favorable in nature to get to a state of higher disorder, randomness, or chaos. And the word they use for randomness or disorder or chaos is entropy. Sounds like enthalpy, but it's not the same thing. Entropy means disorder. They give it the letter S. S is a favorable thing. You want chaos. Messiness is natural. It is good. Chaos good. Positive delta S is favorable in nature. Chaos good. Energy bad. Chaos good. Thermodynamics. Piece of cake. So, if you're trying to figure out the sign for delta H, the enthalpy term, look for the energy in the equation. So if I find the energy in the product side, well, that would mean it's an exothermic process that's favorable. It's a negative delta H. And if they didn't have the equation with energy term in it, you could always just consider the system. Did it get hot or cold? Okay, if it feels warm to you, the system is giving away energy. It's being exothermic. You're never part of the system, you're always part of the surroundings. So if the temperature's increasing, you feel that heat coming into you, that's an exothermic process, it's favorable. But if it feels cold to you, that system is stealing your energy. Energy is going from you into the system is absorbing energy, that would be endothermic, it's unfavorable. To determine the sign of delta S, the entropy term, consider the phases. Look at the products, look at the reactants. You say, okay, well, solids, they're very orderly, liquids are somewhere in the middle, and gases are totally random. So solids have a 3-dimensional crystal lattice, a very orderly pattern, and gases are totally random. If I'm moving this way, solid to liquid, liquid to gas, I'm increasing my chaos. That's favorable in nature. If I'm moving the other way, I'm decreasing my chaos. That's unfavorable in nature. So, for example, if I've got ice turning into water, ice melting, I'd say that's a positive delta S. I'm increasing my randomness. That's a favorable change. But enthalpy changes, the delta H value, and entropy changes, they're occurring simultaneously. And they might work together, and they might work separately. They might work in the same direction, they might work in opposite directions. If I go back to my equation at the top here, add energy into it, it takes energy to melt ice. So H2O solid plus energy would go to H2O liquid. Well, energy being on the left, that's an endothermic process. That's a positive delta H. That's not favorable. Even though I'm increasing my entropy, going from solid to liquid. So here, I've got competition going on. The laws of thermodynamics don't always work together. So there are 4 possible combinations for changes in enthalpy and changes in entropy. You could have them both favorable. An exothermic reaction with an increase in chaos. You could have neither of them favorable or both of them unfavorable is a way to say that. You're absorbing energy and you're losing chaos. You could have a favorable change in enthalpy. You could be releasing energy, but losing chaos, negative and negative. Or you could have an unfavorable absorption of energy, but you're gaining chaos in the process, positive and positive. We'll come back to these four individually, probably 4 separate videos. A scientist by the name of Gibbs figured out how to mathematically relate the first and second laws of thermodynamics. Gibbs described, if you put these equations together, or these terms together, if a reaction continues by itself, once you light it and it keeps going, you give it activation energy, it keeps going, they call that a spontaneous reaction. The term spontaneous, it's not what it sounds like in the normal context of the word. For chemistry, spontaneous means it keeps going. So if I light a Bunsen burner, that flame continues to burn as long as I provide it with fuel and oxygen. It's burning continuously by itself, spontaneously. It didn't light itself, but it keeps burning. So Gibbs came up with an equation, and there are a couple ways to remember that equation. Girls have true sensitivity, guys have no true sensitivity. Maybe that's insensitive in today's politically correct world, but it helps you remember. The G, the H, the T, and the S. No is for a negative sign. So your equation is delta G equals delta H minus T delta S, where delta G, that's the change, delta's change, in the Gibbs free energy. Delta H is the change in enthalpy. T is the temperature, it's in Kelvin, and that's important because it's never a negative term. It's always positive. The lowest possible Kelvin temperature is 0. And delta S, that's your change in entropy. Now, we're going to do some math with this over the next couple days, but right now, this is more like math proof stuff. So it's like logic, math without the numbers. Delta G, if it's negative, it means you've got enough energy left over when you consider changes in enthalpy and entropy that there's enough energy still being released to use it to initiate the next reaction. The process keeps going by itself. Negative delta G means the process is spontaneous. One of the ways I like to think about delta G is delta G, it's what's left over from delta H after you subtract off losses from entropy changes and temperature mitigation. That's oversimplification, but it's one way to think about it. If delta G equals delta H minus T delta S, whatever is left over of delta H, if that's still negative, you have enough energy to keep things going. A positive delta G, on the other hand, means that the reaction, it's going to stop as soon as you stop giving it energy. It's not spontaneous. You can make this reaction occur, but you have to keep feeding it energy in order for that to happen. So negative delta G is spontaneous, positive delta G is not spontaneous. When you have a reaction that is spontaneous, whatever was favorable, whether it be delta H or delta S, that's considered a driving force. So I'm going to pause the video here. Actually, I'm going to start a new video, and we're going to go over the 4 possible scenarios, okay? I'll do a video for each of them. So stay tuned. Go to the next.